Hi, in this video what I want to do is quantitatively show you how to calculate what the angles will be when light travels through an interface of a different index of refraction. So let's take a look at this first example here. And imagine that we have a light ray traveling this way into an interface where it meets glass, like that. And one of the things that's really important for this is to draw this sort of normal line to the interface. It's always going to be 90 degrees from the interface, and we're going to measure the incoming angle, or the angle of incidence, with respect to that dashed line. So this angle of incidence will be 30 degrees here. Imagine we're coming from air with an index of refraction very close to 1 into glass, and let's say this glass has an index of refraction of about 1.5. What will be the refracted angle? How do we calculate that? We calculate that using Snell's law, which is given here. So this is the index of refraction of the first material, the incident angle. This is the index of refraction of the second material, and the refracted angle. So we're just going to try to work with this here. So let's go ahead and plug these values in. So N1 in air is just 1.0. And the sine of our angle, we say it's coming in at 30 degrees. And the index of refraction of glass is 1.5, we said. And now what we have here is the sine of the refracted angle. So that's the unknown. We're going to leave it like that. So in order to solve for the unknown, what I can do is I can say 1.0 sine 30 divided by 1.5 is going to equal the sine of theta r, like that. Now, if I want to get this angle, theta refracted, what I can do is just basically take the arc sine of all this material here. So I can just say something like this. The arc sine of this material, 1.0 sine 30 degrees divided by 1.5. And if I take the arc sine of that, that'll give me the angle of refraction. So let's plug some of that stuff in. So I take 30 degrees, I take the sine of it, that's 0.5. I divide that by 1.5, and I get 0.33. So this is the arc sine of 0.33. So 1/3, like that. And if I take the arc sine of that, I get an angle of 19.47 degrees. Probably more precision than I need, but 19.47. Well, let's look at that. So 19.47 is going to be less than this angle here, right? So it's not going to go straight through like this. What it's going to do is it's going to bend toward the normal. So it's going to basically go something like this, where this angle here is going to be about 19 degrees, something like that. So it's bending a little bit toward the normal. This is what we talked about in the previous video. When you go into a material with higher index of refraction, you're going to bend toward the normal. So let's apply Snell's law in the opposite way. Let's imagine now we're going from water. Let's say this is a tank of water on the left. Index of refraction is 1.33. And we want to know what happens when the light ray, which is coming in at an incident angle of 20 degrees, now enters into air. It passes through this interface, and air has an index of refraction of approximately 1. What is the refracted angle here? And again, we're going to use Snell's law, which is given there and would be given in the formula sheet on the equation, on the exam. So let's try this. So let's go ahead. So the index of refraction of water is 1.33. The incoming angle, or the incident angle, is 20 degrees, like this. It's going to equal the index of refraction of air, which we'll say is approximately 1 for our purposes here, times the sine of the refracted angle, like that. We want to solve for the refracted angle, so we get 1.33 sine 20 degrees, all divided by 1.0. And now if I take the arc sine of this, the inverse sine, like that, that will give me the refracted angle. And I can punch these numbers in. So I can take 20 degrees. Let's take the sine of that. I'll multiply it by 1.33. That equals 0.45. So I get the inverse sine of 0.45, like that. That'll give me the angle. And I do that, and I get something like 27 degrees. Okay, so let's sketch that out. So it comes in at 20 degrees, and it goes out at 27 degrees. So it doesn't travel, straight through. It doesn't travel straight through like this. It actually bends away from the normal. So it's going to bend somewhat away from the normal. I'm exaggerating there, but this angle is going to be 27 degrees. So what it's going to look like is something probably a little bit like that, So this angle is going to be 27 degrees. That's the refracted angle. And this again follows the general rule that we talked about in the previous video, where we just conceptually went over what happens when you travel from one medium to another in refraction. If you go from a high index of refraction to a low index of refraction, you'll bend away from the medium. And if you go from a low index of refraction into a high index of refraction, you'll bend toward the median line, right, like that. Okay, hopefully this was helpful. In the next video, I'll talk about the critical angle and total internal reflection, which is one more case that you need to quantitatively know for the upcoming exam.